Okay, morning. Let's get started. Okay, for those online, so we had some technology trouble with the projectors, so that's why we're slightly delayed at the beginning here. All right, let's continue on the first order ODE. Okay, so it seems like been a little while from previous two lectures. So let's do a very quick summary so far regarding what we have done about first order ODE. So far we have dealt with, can you please stop chit-chatting? And so we have dealt with the following format of first order ODE. Specifically, we have dealt with two different cases. The first case is when the Q of X equal to 0. We call this is homogeneous case. The second case is when Q of X is not 0. So when Q of X is 0, the method we use to solve this ODE is called the separating variable. When Q of X is not 0, the approach we solve this so-called non-homogeneous ODE the approach we use is so-called integrating factor methods, which is what we covered before the midterm. So let's take a look at one more example regarding this integrating factor methods, and then we can get on to a more variety of first order ODE. So bearing in mind, so far, this is a, I see, let's put a keywords here, sorry, missed the keyword. So far we have dealt with, okay, the two cases, they're all linear, okay, first order ODE. The cases that we're going to look at today, okay, after the first example, it's actually not necessarily going to be a linear one. Okay, so let's take a look at this case number 2. Look, one more example regarding this integrating factor methods. Here's the first order ODE. On top of that, we're also giving an initial condition, y of 0 equal to 1. So when you look at this question, your objective to solve it. So first step, that's the more you learn, right? And the first step for you, what you also is to identify what kind of question is this, what kind of a differential equation is this, and then think about the approach that you should use to solve this type of differential equation. So this obviously is a first order one, right? and it's obviously it's actually also a linear one. So the first step, as we mentioned, in order to use the integrating factor method, the first step is to normalize this equation or to standardize this equation so that the coefficient for the y prime is 1. Then you can use the integrating factor method. So whatever you want to call it, standardize or normalize. Basically, you're dividing 1 plus t squared by both sides of the equation. And now you get y prime plus 4t over 1 plus t squared times y. And then this is 1 plus t squared to the power -2. So once you divide, you get this is 1 over that term to the power 3. And this is obviously a linear first order ODE, although I mean this is not a constant, but that's okay. So the next approach is to apply this integrating factor method. To apply this method, right? So number one is, you got to identify this function here is your P of t, and this function here is your Q of t. So your function, the independent variable here is instead of x, from the t. So you got to be a little bit flexible here. As I recommended, I don't want you to memorize any formulas rigidly. I want you to be able to follow the procedures of the integrating factor methods. So the procedures is, once you are at this stage, then you multiply that integrating factor . In this case, it's a sigma t, it's a Greek letter sigma. And then you get sigma t y prime plus sigma t, it's a big term, but you can get it over here. So the integrating factor method, the idea is you want to find appropriate sigma t, this integrating factor function, so that your whole left side can be written into sigma times y prime. So that's the idea. And we have demonstrated in order for you to write the left side from here to here. Okay, so from here to here. So we need sigma prime, which is d sigma over dt, sigma is function of t, equal to the sigma of t times 4t plus 1t squared. So we need to solve this one to get a sigma function, and the solution of that will enable you to write the whole left side into sigma y prime. And sigma prime, the term that equals to this term here is basically this term here. And this term essentially is your sigma times P of t, right? Times this coefficient for the one. And that's clearly a function that you can solve using separating variable approach. So you can separate the sigma and then t move to the other side. So from here to here, you separate the variable. So now you can integrate both sides to solve for sigma. Left side give you ln sigma. So over here, you don't have to be very rigid now. So technically, you should put an absolute sign here. But remember what we said is we just need one function sigma. So we don't have to be bounded by that absolute sign. So ln sigma equal to the result of this integral. And this is where inevitably you're going to have to exercise some of your old integration technique. Now, there are some very frequently used technique. Part of that is this substitution rule. And of course, there are straightforward integrations. There might be also integrations deal with square root or sinusoidal. But in this class, when we have an exam on this kind of question, okay, so what I typically, I'm not going to focus too, you shouldn't worry too much about am I going to have a very complicated integration or not? So it's more just focusing on the approach, whether you know the approach or not. Okay. So over here in this question here, this one you do need to use the substitution rule at here. Okay. So for the right side here, so that t dt can become 2t dt can become dt squared. So then you can put a 1 into this differential, which you don't really change that. So now anything after differential operator, the 1 plus t squared is the same as this bottom 1 plus t squared. So it's basically the substitution. Your typical approach is to let u equal to 1 plus t squared, and then you follow that, right? If you come more comfortable with that, that's fine. That's what I typically will do instead of letting the u equal to that. So then the result of this integration is just 2 to what? 2 ln 1 plus t squared, right? Okay, so then this is your ln sigma. So your sigma equal to 1 plus t squared, and then square here. Any questions on the results that are here? This is your function sigma of t. And I always encourage you to verify. So remember that the purpose of this step here is to find an appropriate sigma function so that your whole left side can be written as sigma y prime. So if you're not too sure whether you get the right sigma or not, which is also very good to verify, so just multiply the sigma with your y and then take derivative of that using product rule. See if you actually get back to the expression like this. Okay. So that's the idea. So in this case, of course, you will. Okay. I'll just write down here. So verify if necessary. Right. It's up to you. If you're confident, then you don't have to. So now so now the original function, right? The original differential equation becomes sigma y prime equal to the sigma of t multiplied by this 1 over 1 plus t squared to the power of 3. So equal to sigma of t 1 over t squared cubed. So time to substitute the sigma into this expression and here. So 1 plus t square times y. And I'll write this in terms of d over dt. This is 1 plus t squared, 1 over this. Squared. So you can cancel part of this term in here, which you get 1 over 1 plus t squared. Okay. You multiply the dt to the right side. So you get d 1 plus t squared times y squared here equal to 1 over 1 plus t squared dt. And now you integrate both sides. An integration of d anything, d a bracket, whatever inside the bracket, will give you back. Right, that's basically the antiderivative. So it will give you back this term inside the bracket. The integration of the left side. Now this sometimes does needs a little bit of skill or memory. So the integration of 1 over 1 plus t squared. Not sure if you remember what is the result of this integration. And you actually done an assignment in 248 on this one. We did an example in the class. Tan inverse, right? Yeah. So it's okay you don't remember. As I said, if I don't teach this course, I probably don't remember either, right? So, plus a constant c. But you do need a constant c at here. Where is the c from? The c can come from either this integral or this integral, but anyway, so we do need a constant c at here. So then we can apply the initial condition. So finally, you solve for the y. Okay, so that's what we're aiming for. We're trying to solve for the y function. So we get tan inverse t over 1 plus t squared and then c over 1 plus t squared. That is the expression for y. And the constant c's value can be determined by the initial condition. Initial condition is y of 0 equal to 1. So that means you let the t equal to 0, and then your value of y should be 1. So let's plug in t equal to 0 for each one of the term. Tan inverse 0 is 0. So the first term is 0. The second term is c over 1. So that basically gives you c value equal to 1. So finally, your solution for y of t equal to tan inverse t that's a solution. So this is a proper procedure of integrating factor methods. So I encourage you at this stage, try not to skip any steps. Try to do every one of the steps, and understand the purpose of each one step. So later we're going to learn, this is what we call a general solution. And this is called a particular solution because it's particular to certain initial condition. Any questions on this linear non-homogeneous first order ODE using integrating factor approach? So good. Okay. So that summarizes, right? So bear in mind in your head. So what we have done is the two cases, and the two cases are from the so-called linear first order ODE. So now let's look at in particular maybe three more actually. Okay, so today we're not going to cover all three of them. So three more types of first order ODE. So notice that I don't have the keywords linear anymore. Okay, so the three types that we're going to look at next, they're not necessarily actually linear. Okay, so I say most of the time they're actually non-linear. But we're going to look at it how we can solve that three types of that first order ODE analytically or mathematically. The first type is called separable equation. So sometimes you probably will find the wording duplicate with some of the wording that you just learned, right? So separable equation. Okay, so let's look at what is separable equation. So for the separable equation, it takes the formats like this. So y prime equal to a function of x and y. And then this function f of x, y just happen to be able to separate into two functions. One function is all about function of x, and the other function is all about function of y. So this function here can be separated into these two components. If you can do that, or if you happen to have an equation just like that, then this type of equation is called separable equation. So let me show you an example here. So sometimes the equation given to you may not be very obviously or apparently a separable one. So you need to manipulate this a little bit, and then you will see, okay, that's actually separable. Okay. So for example, y prime equal to x times e to the power x plus 2y. All right, so if let's say if you have this kind of equation, right, your institution has to tell you, so what kind of equation is this? Is this a linear or is this a non-linear? Now that's the first step you probably want to identify. Identify whether it's linear or non-linear. It's straightforward. You have the standard format. You try to use a cookie cutter, right, to identify this one. And obviously it's not a linear because you have an exponential term in here, and it's non-linear. Then and the next step requires a little bit of experience, right? Is okay. So what we can do with this sort of a non-linear. Now, what type of this ODE, first order ODE, it falls into? So in this case, we can manipulate this question, especially the e to the power term, because this is e to the power a plus b. So you get basically e to the power of a times e to the power of b. So obviously, you have multiplication of two functions. And the first function in here is a function of purely variable x. The second function is function of purely variable y. That fits into this type 1 separable equation format. Okay, so I mean, so in this case, you might ask, how do I know? A lot of time experience and practice, right? That's how you can quickly identify. So let's take a look at another one here. So let's say you have a function like this. So it's written in this kind of format. And your first step is to identify, is it a linear or is it a nonlinear? Okay, so if you go down that route, which is the correct direction, and you should be able to identify this as is a linear or nonlinear. The linear equation or nonlinear equation? Linear, right? Yeah. So once you identify this as a linear, probably what you should have done this step is you move the y here and c here, okay? And then you also identify it's not only just a linear, but also not homogeneous. So I think chances are you're going to choose this integrating factor approach to solve this question. But you're not going to choose anything else. Of course, sometimes you got stuck. You said, okay, I don't know whether it's linear or not. Then you say, can I try the separable equation approach? So you're looking at the left side here, or the right side here, and you try to see, is it possible to separate this into a multiplication of an x function and with a function of y? So do you think you can write this into a multiplication of two functions like this? I see. Yes, you can't. No, sorry, no, you can't, right? So you can't because there's 3x minus y added here. So I think what I'm trying to demonstrate is this is sort of the way of solving questions, right? You go down this direction, and then it doesn't work. So that should actually tell you, okay, maybe I should try the other direction, right? And then you go back, and then maybe you'll see, okay, that's actually linear. That's how you try to find the right direction to go, right, at the end. So not all left side can be read, okay? So let's give you an example right here. And this example, let's formally try to solve this. So here's another differential equation, first order differential equation, ODE. If you exercise the thinking first step, is that a linear or nonlinear? I think by this stage, you should be very confident to quickly identify this. It's definitely not a linear, right? And the next step, if it's not a linear, then none of that approaches we have learned integrating factor will work over here. So, I mean, we haven't learned other types yet. Then say, is this an equation that we can separate on the left, on the right side? So you can take a look at it. Separating here, well, I guess I have 4x at here, and then I get, and this term at here. So that's clearly a multiplication of two functions. One is a function of x, and the other is a function of y. So that's a separable equation. Then you apply the approach to solve this separable equation. So how do I solve for separable equation? And solving separable equation, the approach to use separating variable approach. Okay, that separating variable approach, if you recall, we use that when we solve this. What is that? The homogeneous first order linear ODE, right? So over here, the dy is basically dy over dx. So now we're separating variable. Separating the variable for separable equation. So we'll move all the y terms together, move all the x terms together. 1 plus 2 to the power of y, e to the power of y, dy equal to 4x dx. And then integrate both sides of the equation. there's no trick in terms of this integration and here. So the left side gives you y plus 2e to the power y. The other side gives you 2x squared plus constant c. Okay, at this stage, remember you're trying to solve for y. However, based on the results at here, we actually cannot get an expression specifically for explicitly for the y. So what you're getting here is a case we have mentioned before. You got an implicit solution. And because the e to the power y term in here, so you want to be able to get an expression for the y. However, we do need to solve for the constant c using this initial condition here. So apply the initial condition. At y of 0 or y of x equal to 0, so that's x equal to 0, you get y equal to 1. So 1 plus 2e to the power y equal to 2 times 0 plus c. So c equal to 1 plus 2e. Finally, plugging the c back into the implicit solution. That's basically everything you can do. You could do for that particular question. Okay, so again, I did think from the bigger picture, right? So you have a huge category under linear first order ODE, and then this is the second, let's say call it the category separable first order ODE. Right. So let's take a look at one more example on this separable equation type. Let's say we have this following first order ODE. And now you want to identify what approach that we can use to solve this ODE at here. I want you to take a look at it, before we solve it. Maybe I want you to tell me, based on your observation, what kind of ODE is this? And what do you think, and what direction do you think you wanted to go to solve this one? Okay, so first question, as I asked, is it a linear or not? So don't be disguised by the appearance of this one. Right? You can always try to move around terms. Okay, yeah, it's linear, right? Yeah. Is it a homogeneous or is it a non-homogeneous? Is it non-homogeneous? Huh? What do you say, Rishi? Homogeneous. So homogeneous basically means when you move all the terms to the single side, is equal to 0, right? Okay. So then you already identified, so dr over d theta, okay? If I write it according to the standard format of the first linear first ODE, what I would get is dr over d theta minus b sine theta over 1 minus b cosine theta, and then r equal to 0. So you get this kind of standard writing of this equation. So this is a first order. This is a linear first order homogeneous ODE. And then immediately what follows from this type of ODE is to use the separating variable approach, right? Separating variable approach. So separating variable, basically you rewrite this term back into the right equal to the left format. And then you separate the RD theta together. Then you solve this equation. However, my intention actually, okay, is to give you an example that as long as you can write this equation, the original equation, in this format, and when you observe the right side there, okay, and the right side is also a function of theta times a function of r, right? So it is also a separable equation, basically. So as you can see, sometimes things overlap, right? Yeah. But as long as you can identify the proper format, apply the separating variable approach, and you'll get the right answer. So basically, this is also a so-called that separable equation. So categories do overlap sometimes, including each other. So all roads lead to Rome, right? That's basically what happens here. All right, any questions on this separable equation, separable type of ODE? So I think the solving approach is fairly straightforward. So now let's take a look at the second type. I said there are 3 types. The second type is called homogeneous equation. So type 1 is called separable equation, and then this type is called homogeneous equation. So the name somehow, it's like we're running out of names for mathematical functions here, because we already have a name called homogeneous ODE, right? Yeah. So now we have another name which sort of already overlap to that name. It's called a homogeneous equation, but it is very different. Okay, so this one here, what the equation you will see is very different from that homogeneous ODE. So let's take a look at what exactly this homogeneous equation looks like. Okay, if you have a first order ODE in the format of a dy dx equal to f of xy, then we call this is a homogeneous equation. If the following condition is satisfied, and the condition is, again, you look at this function f of xy. So the function f of xy equal to lambda f of lambda x lambda y, and lambda is constant. So if that function f on the right side is equivalent to this expression, then that equation, that ODE equation, is called homogeneous equation. And the name actually comes from the format of the function here. So we call this type of function called this type called the homogeneous function of degree 0. Degree 0. If hang on a second here. I think I missed one. Sorry, I missed the term here. So this is n here. Okay, this is n. Lambda to the power of n. So we call this is n here. Okay. We call this kind of function homogeneous function of degree n. So what's n? N is an integer, so n equal to 0, 1, 2. Right? So any of the integer numbers. And the simplest type, right? So the simplest is n equal to 0. And when n equal to 0, the lambda to the power 0 is 1, right? So you get f of x, y, just simply equal to f of lambda x, lambda y. And that's actually one we'll see some of the examples of where we're going to deal with these things here. So now you can see, just try not to be confused by the names of this. Maybe try to somehow in your mind, try to memorize the behind the name, the pattern of this type of function, of the type of the equation. And the pattern is purely based on what this function f of x, y looks like. Right? In this case, you can write this function f x, y in a format like this, or in the simplest format like this. So let me show you an example. So let's see if I have a function f x, y equal to this. So let's say I have function f of y like this. Then obviously you cannot separate it because it's all tangled together. But I can try this. So let's see if I try replace the x with lambda x, replace the y with lambda y. Let's see what do we have. Okay. So x replaced with lambda x, y with lambda y, and lambda x squared, lambda y squared. You got lambda everywhere. So the top you got lambda square xy. Bottom you also have a common factor lambda square. And then cancel. So you end up with exactly the same as f of xy. So that conforms with the definition of homogeneous function of degree 0, right, in this case. So this is basically, you can conclude that this function f of xy is a, you don't have to write it every time, is a homogeneous function of degree 0. Okay. Right. Similarly, I want you to try manipulate this function, for example. And you can manipulate this function, and you will get the same conclusion. It's also a homogeneous function of degree 0. As you can imagine, sometimes you'll end up with a lambda to a certain power term here, not just necessary to the power 0. Right, so then you get a homogeneous function of degree out of degrees. So we'll look at how do we solve this type of homogeneous equation, okay, this type. And then there's the third type. And so that should conclude the first order ODE. Any questions? Thank you.